السلام عليكم ورحمة الله يعطيكم العافية شباب صبايا. اليوم راح نبلش بشابتر 14 internal flow. بهذا الشابتر we will talk about the fluid flow in conduits. So starting with the conduits maybe of circular shape as shown in the sketch here to the left, or in other shapes such as the rectangular ducts as in the sketch to the right. Here we will be interested in learning more about the friction, about the pressure drop, and the head loss. The head loss, this term we learned back in chapter 12. In this chapter we will learn about the details of how to evaluate the head loss, whether it's major head losses or minor head losses. Besides, we will learn how to calculate the pumping power requirement to compensate the pressure drop. Okay. Okay. First of all, remind you of the mass flow rate that we have used frequently through this course. It's defined as the density times the average velocity times the cross-sectional area. Also, the average velocity times the cross-sectional area is also the volume flow rate. In case the velocity was variable with the area, then the integral form is applied in this case. The average velocity may be calculated through this equation. In case of circular pipe, then the average velocity reduces to this form. For the laminar flow in pipe, fully developed flow, the profile will look like this, parabolic profile. In this section 14.2, one of the classification of the flow is the laminar and turbulent flows. The laminar flows, the flow is characterized by smooth streamlines and highly ordered motion, while in turbulent flow, it's characterized by velocity fluctuations and highly disordered and chaotic motion. The transition is the region or the regime in between the laminar and the turbulent. It has characteristics from both the laminar and turbulent flows, so it fluctuates between the two. Most flows in practice are turbulent. Okay. Examples of the laminar and turbulent flow, as we can see, the gases coming out from a candle. At the beginning, they're laminar. Once the wind accelerates the flow, the transition occurs and it goes to the transition and the turbulent flows. Similar here to this dye injection. If the laminar flow, then the dye trace will look something like this, while in the turbulent flow, it will look something like this. How it's laminar or turbulent depends on different parameters. One of them is the velocity of the flow itself. The velocity of the flow itself. The parameter that will be used to determine whether the flow is laminar or turbulent is the Reynolds number. The Reynolds number represents the ratio between inertial forces to viscous forces, and is given through these two forms. There are other forms based on the mass flow rate, which can be related to the average velocity to the mass flow rate or the volume flow rate, as we showed in this slide here. But the forms here are in terms of the average velocity, the diameter, and the kinematic viscosity or the dynamic viscosity. So the critical Reynolds number is the Reynolds number at which the flow becomes turbulent, in this course, for the laminar flow, it will be considered the flow to be laminar if it's less or equal to 2300, between 2300 to, let's say, that's something debatable. Some textbooks refer to that as the 3000 or 4000. In here, it shows as the 10,000. So Here, the laminar flow, the transitional flow, if it's greater than the 10,000, then that's when it's for a turbulent flow. For the purposes of this course, we will consider below 2300, we will assume the flow is laminar. Greater than 2300, that we will treat it as turbulent flow, and the equations for the turbulent flow apply. The Reynolds number, as in the previous slide, it was based on the diameter. In case the pipe or the conduit was not circular, then we introduce a hydraulic diameter. The hydraulic diameter is defined as 4 times the cross-sectional area divided by the wetted perimeter. So in the case of circular tube, we can check that the hydraulic diameter is the same as the diameter. While for a square duct, the hydraulic diameter is simply the edge length. For the rectangular duct, the hydraulic diameter is, as shown here, twice AB divided by A plus B. The entrance region. The entrance region is defined as the region where the flow properties are developing with the flow direction besides the transverse direction. So as we can see here, the velocity profile is changing with the flow direction, while once it reaches the fully developed region, that's when the flow properties, and so we are talking here at the about the hydrodynamic, and the hydrodynamic fully developed. In the hydrodynamic fully developed, that means the velocity profile does not change anymore in the fully developed region with the flow direction, but it still varies. It still varies with the normal direction, as shown here. How to calculate the length of this entrance region? We will show in a little bit the equations to calculate this entrance region. It's function of some parameters beside the flow regime itself, whether it's laminar or turbulent. The reason why this developing occurs and why this entrance region is because of one of the reasons is the boundary layer region, since the flow enters the conduit as uniform flow, and as a result of the boundary layer and the no slip boundary condition, the velocity of the fluid particles adjacent to the solid surface must take the velocity of that surface, which is in this case it's stationary. That means that the velocity at the wall should be 0, but this process occurs gradually. That's why the velocity profile keeps changing until it reaches its fully developed profile, where it won't change anymore with the flow direction. Now for the entrance region, as we mentioned here, the velocity profile in the entrance region is function of, let's say if this is x and r, so it's the u is function of x and r. In the fully developed region, the u is only a function of r. So here, the hydrodynamically fully developed condition, that's the du dx is 0, and so the u is only a function of r. What other properties that do change? The wall shear stress, which we learned in the previous chapters, the wall shear stress for Newtonian fluid, which is function of the du dy at the surface. So since the velocity profile won't change anymore in the fully developed region, then the wall shear stress becomes constant, while in the entrance region it keeps changing, reducing until it reaches the fully developed region. That's when it becomes constant. Okay, these lines here represents the velocity boundary layer, and the thickness of this is called the boundary layer, the velocity boundary layer thickness. For the hydrodynamic entrance region length, it's given by the following two equations. For if we have laminar flow, then it's approximately equals to 5% times the Reynolds number times the hydraulic diameter. While for the turbulent flow, we will consider this as the hydrodynamic entrance region length for the turbulent flow approximately equals to 10 times the hydraulic diameters. 10 times the hydraulic diameter. Now focus on the laminar flow in pipes. For the laminar flow in pipes, those are equations you may check them on your own that what you want to be asked to derive these equations. So we will go, the velocity profile in the circular tube is given through this equation. The average velocity is according to this equation. The maximum velocity equals to twice the average velocity. That's all for laminar flow and circular pipes. The pressure drop is given through this equation, and it's considered the major pressure drop. Major is due to the friction. The major pressure drop due to friction. So it's given through this equation. Those slides are modified to distinguish between the major and the minor. The major and the minor. So the major pressure drop due to losses, or the pressure drop due to major losses, given through this equation. The friction factor, this F, is called the friction factor. For circular pipe laminar flow, it's given through this equation. It equals to 64 divided by the Reynolds number. Remind you that this represents the dynamic pressure, which we learned back in the Bernoulli and the energy equation. The Darcy friction factor may also be given through this equation. The major head losses equals to the pressure drop due to major losses divided by the specific weight, which is rho times G, and it equals to F times L divided by the hydraulic diameter times the average velocity squared divided by 2G. This represents the major head loss. The pumping power required to compensate for this major losses equals, or to compensate for losses in general, equals to the volume of flow rate times the pressure drop due to these losses, which also may be given in different forms, since the pressure drop due to losses equals to specific weight times the head losses, and it also the density now times the volume flow rate equals to the mass flow rate. So any of these forms work, depend on what variables are given in the given problem. Remind you that the volume flow rate equals to average velocity times the cross-sectional area, and the average velocity for horizontal pipe is given through this equation. Okay, so a summary: the pressure drop due to major losses is given through this equation. The major head losses is given through this equation. Okay, now to the question is the pressure drop equals to the pressure loss or the pressure drop due to losses? The answer is simple, no, and we will show this. Recall the energy equation from chapter 12. This is one of the forms. So we can check P1 minus P2 will equal to this, while the delta PL is simply equals to rho G times HL, rho G times HL. So they're not equal. That's the pressure loss equals to rho G HL, while the pressure drop equals to all these terms. So the pressure drop equals to the pressure loss when we don't have pump head, we don't have turbine head, there is no elevation changes, there is no kinetic energy changes. That's when the pressure drop equals to the pressure loss. The effect of gravity on velocity and flow rate. The previous relations for the average velocity and the volume flow rate were for horizontal pipes. If in case we have inclined pipe, then the gravity will have effect, and so the average velocity is modified to this equation. Similarly for the volume flow rate. Okay, so again, the summary here: for horizontal pipe, this is the volume flow rate. For inclined pipe, this is the volume flow rate. In case the theta was greater than 0, theta is shown here. This is the reference for the theta with the horizontal. So in case theta greater than 0, then sine theta greater than 0, and it's called uphill flow. While if theta is less than 0, so that's the opposite, inclined the opposite direction, then sine theta less than 0, and it calls the flow is called downhill flow. Laminar flow in non-circular pipes, the main thing is to find the friction factor. For circular, it's simply 64 divided by Reynolds number. For other cross-sectional uh, conduits or pipes, such as rectangular, elliptical, isosceles, triangular, we have the friction factor is modified accordingly according to the geometry parameters involved in these other shapes. So we need to refer to table 14.1 in case we have non-circular pipes. And the Reynolds number here is calculated based on the hydraulic diameter, which we showed you earlier in this chapter how to get the hydraulic diameter. It's simply 4 times the cross-sectional area divided by the weighted perimeter. Okay, now we move to the turbulent flow in pipes. The turbulent flow in pipes, again, to remind you, the turbulent flow is characterized by highly disordered motion velocity fluctuations. Swirling, these fluctuations and swirling regions of fluids called eddies, and they appear throughout the flow. The turbulent velocity profile, this is the laminar velocity profile, while this is the turbulent flow velocity profile. We see that it's more flattened shape. That's for the turbulent velocity profile in its fully developed shape. Okay. We showed for the entrance region length, we agreed that it approximately it equals to 10 times the hydraulic diameters. That's in case we have turbulent velocity profile. The friction factor for the turbulent flow is found through this implicit equation, which is called Colebrook equation. And it's applicable for smooth and rough pipes. As we can see here, a new parameter appears, which is called the relative roughness. It's the epsilon divided by d. Here, this is called the relative roughness. Roughness here, epsilon, it has the length units. So here it's given either the foot or the millimeters, which you need to pay attention when you get the values for the epsilon. Make sure that you get the correct unit system, since it's given in both feet and millimeters. There's an approximate relation to avoid the implicit relation, as we can see here. It's implicit. An approximate relation, which is explicit, is the one proposed by Haaland, which is shown here. Okay. Now, this Colebrook equation is plotted on the Moody chart to avoid the complications in solving such implicit equation. While nowadays there are, with these advanced calculators, they are capable of solving such equation rather than use the iterations to solve for the friction factor. Or we can simply use the Moody chart. The Moody chart, which is I highly recommend that you get familiar with the Moody chart. In the Moody chart, we can see that the Moody chart, there are 4 parameters. We have the Reynolds number here in the bottom x-axis. We have to the right y-axis, we have the relative roughness, the epsilon divided by the hydraulic diameter, while to the left, we have the friction factor, which has different names, as also Darcy friction factor or Darcy-Weisbach friction factor, or the coefficient of resistance, or simply the friction factor. So as we can see here, this is the laminar flow, which is for circular pipe, that's the 64 divided by Reynolds number, while here the region where the turbulent flow starts. So where we can get the value for the friction factor from this chart. Okay, this is how to use the friction factor. The Moody chart, it shows you how to use the Moody chart. So for the Moody chart, we always need 2 parameters, Reynolds number and relative roughness parameter, and then we can get the friction factor, or the Reynolds number, the friction factor, and the Reynolds number and get the other parameters. So we always need two parameters to determine the third parameter. Okay, types of fluid flow problems. We determine the pressure drop, flow rate, determining the pressure drop. If the pipe length, diameter are given for a specified flow rate or velocity, we can get the pressure drop. Determine the flow rate when the pipe length and diameter are given for a specified pressure drop or head loss. To determine the flow rate, if the pipe diameter are given, then we use this equation. These equations are called Swabian-Jain equations. Determine the pipe diameter when the pipe length, flow rate are given, then for a specified pressure drop, then we can use this equation. So that's to avoid the tedious iterations. We can use these relations. This is for the head loss in case the pipe length, the diameter are given for a specified as well volume flow rate. So these are the three types of problems encountered in the pipe flow. Now we finished with the major losses, which was due to the friction, mainly due to friction. The minor losses are due to the components, the different components in the piping system, such as fittings, valves, as we can see here, bends, elbows, tees, inlets, exits, enlargements, and contractions. So those result in additional losses called minor losses. So the losses are divided into two parts: major losses, which we learned in the previous two sections, that's due to friction; the minor losses, which are due to these different components in the piping system, and the total losses is the sum of these two. The sum of these two. The minor losses is given through this equation. The minor losses equal to some new parameter we will talk about in the next few slides. It's called the loss coefficient times the average velocity squared divided by 2g. That gives us the minor head loss. So, and the minor head loss is also related to the minor pressure loss. So the minor pressure loss divided by rho g, that gives us the minor head loss. So this the loss coefficient related to the pressure loss through this equation as well. And this is the minor head loss. Again, it equals to the loss coefficient times d squared divided by 2g. Every component may be represented by equivalent length. So assume that this is very common to be used with the design in the design of the piping system for sanitary systems and for HVAC, the air conditioning systems, is to use something, a concept called equivalent length. What do we mean by equivalent length? It's the length that must be added to the pipe to replace the component, So that's simply by assuming that this component is what is equivalent in pipe length. So we equal the loss that this component causes by a major losses, and by this we calculate the equivalent length. The equivalent length would be simply the diameter divided by the friction factor times the loss coefficient of that component. The total head loss equals to the major head loss plus the minor head loss, which given through these two equations. The sum, that depends on how many components we have. So we need to add the sum. While the sum for the major losses depends if we have different pipes of different diameters. Means, in that case, different diameters mean different lengths, in general, different friction factor, and different average velocities as well. The total head loss, if the diameter is constant, that means that the average velocity according to the mass conservation equation for incompressible flow will be the same. the friction factor will be the same since the velocity is the same. And it's the same diameter, the same pipe as well. So this equation reduces to this form in case the diameter is constant. Now the tables to find the loss coefficient are shown in this table 14.4. For the pipe inlet, the loss coefficient equals to 0.8, sharp edged, it's 0.5, well rounded, it's 0.03, slightly rounded, it's 0.12. As we can see, when it's well rounded, the loss coefficient reduces substantially compared when it's slightly rounded, and even compare when it's sharp edged. For the pipe exit, it equals to the kinetic correction coefficient that we introduced back in chapter 12. Sharp edged, rounded, it's the same. It's the same. Now, for the sudden expansion and contraction, and for the sudden expansion, we have this equation. It equals to the alpha, the kinetic energy correction factor or coefficient, times 1 minus d squared divided by d squared. While if we have sudden contraction, then we have this chart to find the loss coefficient, which is function of the diameter square ratio, and then we can find the loss coefficient. In case we have not sudden expansion or contraction, if we have gradually, then we have the loss coefficient given through these two sketches, which is again is function of the angle of gradually expansion or contraction, and the diameter ratio between the contraction or the enlargement, sorry, and the contraction. Bends and branches are given here. You may check this table and carefully. These are the valves, different types of valves. We have globe valves, angle valves, ball valves, swing check valves, gate valves, whether they're fully open, half closed, quarter closed, depends on the closure of that valve. The more the closure is, then the higher the loss coefficient would be. Okay, again, this is to remind you of the equation that was shown here. That's for the sudden equation. This is in terms of diameters, which is the same in terms of areas, since the factor is constant. The factor is constant. Okay, this is shown here how the pressure losses happen with the expansion, and explains the idea from the loss coefficient. Okay. Now for piping networks and pump selection, if we have branches, then it's the same as in electrical circuits. The flow will be divided into these branches. The pressure loss between the junctions must be the same no matter what branch we take. Okay, that makes sense because as we learned back in chapter 11, the pressure at a point cannot have more than a value. So it's the same. It's independent of direction. The pressure at a point is independent of the direction. So here, let's assume this is branch 1, branch 2, then HL1 equals to HL2. Why? Since the delta PL1 equals to delta PL2. Why? Because the pressure at A and the pressure at B are the same no matter whether we took branch 1 or branch 2. While the volume flow rate at A equals to the volume flow rate at branch 1 plus the volume flow rate at branch 2, and then they combine together to equal the volume flow rate at B. Okay, these are the laws here, which may be related to find either the velocity. This represents the velocity ratio between 1 and 2, while this is where 1 and 2 represents the branches that the pipe took, and here in terms of the volume flow rates. Piping system with pumps and turbines, and the energy equation from chapter 12 apply, and then when we can find, again, remind you of the pumping shaft power or the electrical power from the pump motor, similarly for the turbine generator. This here represents the characteristic curves of the The characteristic, this represents the characteristic curve of the pump which comes from the manufacturer. That's for the pump head versus the flow rate. While this dashed line here represents the system curve. This system curve comes from the energy equation, The intersection between the characteristic curve and the system curve is called the operating point, That's all for chapter 14. يعطيكم العافية. نشوفكم بالnext lecture إن شاء الله.